We discussed in last lecture this equation, that is T by J is equal to tau by R is equal to G into theta by L, right? So, and this equation is called as torsion equation, and we discussed it. Now in this, J is very important component, and J is called as polar moment of inertia. And for hollow shaft, J is equal to pi by 32 into d to the power 4, and for solid shaft is equal to pi by 32 d to the power 4, and for hollow shaft is equal to J is equal to pi by 32 into capital D to the power 4 minus small d to the power 4, right? Now in this R component is very important, and it is not written what do you mean by R, but as far as from the diagram itself we can see from this diagram, right? From this diagram we can see that R is the outermost distance from the center, from this end to this end. R is the outermost distance, that is R is the radius of the bar, right? And instead of radius we will say that outermost distance of the fiber from the axis, right? That will be R. Because if we do the analysis for hollow shaft, then there will be two radius. One is the internal radius and one is the external radius. So we'll do the calculation for external radius only, right? Okay. Then next very important topic is strain energy in torsion, and as we already know that work done in straining the shaft within the elastic limit is called as strain energy in torsion. And just like the formula is derived in the same manner what we derived in case of force, U is equal to half into T into theta, where theta is the angular displacement in radian and T is the average torque in Newton meter, right? Half becomes, because when if we apply torque on in a gradual way, right? That is why at the initial pace the bar was experiencing zero torque, but as soon as we apply torque on it, it has experienced T torque. That is why it is the average torque, that is 0 plus T divided by 2. That is why in this case half has come, right? So U is equal to half into T into theta. Okay. Then in the same step, next formula is very important, that is the power transmission by the shaft. And we know that power transmission by the shaft is P is equal to work done per unit time is equal to T into theta, where T is the applied torque, and applied torque is same as the internal resistance, internal moment of resistance, T multiplied by theta, and theta is the angular twist, right? So that is the work done. And we know that power is equal to W upon T. So in the same manner on this side also we done P is equal to T into theta upon T, where theta upon T I can write down as omega. And if I write down the value of omega, then omega is 2 pi n T upon 60. It is in watt. Now please mind it, in this case the units will play very important role, and we have to be very careful about the analysis of this particular power transmission. Now one thing I wish to make you clear in this, why 60 we have written, because the watt means Newton per second, and in this N is in revolution per minute, and that revolution per minute has transmitted into, so we need 1 minute is equal to 60 seconds. So that is why we have written, we divided this entire term by 60 so that we can get the power transmission rate in terms of second, because this is in Newton per second. So that is why we have done 60, and in this case we will put N as RPM only. Okay. Then there are some formulas written over here. One formula is torsional stiffness, and that torsional stiffness is T by theta. See, stiffness is the stiffness is the amount of torque, and that amount of torque which is divided by the per unit deflection. The torsional stiffness is actually the amount of torque required for unit rate of deflection, unit rate of angle of twist. So in this case, that is why torsional stiffness is T by theta. Whereas the second is torsional rigidity, and that torsional rigidity is, I googled it. So torsional rigidity is the amount of resistance a cross section has against torsional deformation. I'll again repeat the line. Torsional rigidity is the amount of resistance a cross section has against torsional deformation. That is, in this case, we can do this calculation by T divided by theta by L. Why theta by L? Because it will depend upon the 1 unit of angle of twist over this much of length. So that is why T divided by theta by L, right? Because it is 1 unit of deflection for 1 unit of length. Then next is the term is polar modulus, and polar modulus is J by R, and J by R term is also very important. We'll understand what is the importance of this J by R term, right? Okay. Then next, strength of a circular shaft. It is already explained in a beautiful manner, but I wish if you should please study this on your own, and maybe in the numerical you have to apply this concept, right? Or we'll discuss this concept into detail during our live interaction, but please study every point of this section. It is very important, and I want you to discuss it, you to understand this, and then we'll discuss it, right? Okay. Now let us come to the other part of the setup. Like in this, just a minute. Okay. No issues. Right. In this is the okay, the importance of J by R. Here it is. This was the equation. This is the T by J is equal to tau by R is equal to G into theta by L. And in this equation, if I take these two parameters, so that is T by J is equal to tau by R, and in this just rearrangement of terms, so that is T is equal to tau into J by R. Or in this, what I understood is, see, tau is the property of the material, and I cannot work with it, I cannot change it, because if somebody has told me that you have to make the shaft of mild steel, then I have to do that, I have to honor his, but I can always play with the geometry of the shaft, right? So that is why J by R term is very important, and this J by R term is called as polar modulus. This J by R term is called as polar modulus. See how it works. Now I have the liberty that this is the area of cross section of the shaft is let us say the length of the shaft is this only, right? And area of the shaft is this fix, like this fix. This is the circular. Now I can, instead of circular shaft, I can draw the shaft in a rectangular manner. Instead of circular shaft, I can draw the shaft in a T section beam manner. Then instead of circular shaft, I can draw the shaft in an I section manner. I section manner means it is just like a railway track. The railway track, if we see the cross section, it is an I section, right? If you see to it, it is an I section. So it is my liberty that what cross section I wish. But in this case, I'll choose the cross sectional shape in which J by R for that particular cross section is maximum, right? J by R should be maximum. So J by R is called as polar modulus. That is why this particular property is very, very important, right? Then this power P is equal to 2 pi nt upon 60. I had already explained, right?